So we had the relationship between tau and shear stress and shear strain, which is tau is equal to G times gamma. And sorry, let me just activate, okay. Tau is equal to G times gamma, and instead of gamma, I can put U1 minus U2 divided by H. If I combine these two equations and get the derivative of tau with respect to x, I end up with this equation. Now, the reason I calculated the derivatives just like carbon nanotubes is because I know this is equal to sigma 1 divided by E, and this is equal to sigma 2 divided by E. So that gives me a new equation 3 in which it's all about stresses. Displacements are now out because I can replace this with that and this with that. So now, now let's look at the equilibrium equation in the differential form. If I take just a very small section of tablet 1 that has a length of dx, and I assume the stress is defined with function sigma x. So on this end, we are at x, and on this end, we are at x plus dx. So if I take this section and I redraw it here, this is what I will have. And all the forces applied by this to the left is sigma x times b, to the right, sigma x plus dx times b, and tau x times dx. I put them in equilibrium. So basically, this force minus that has to be equal to this. And this gives me this differential equation of equilibrium. I can do exactly the same calculations for 2. And the only difference is that in this case, I'm going to get the derivative times b is equal to minus tau x. That's because the direction of tau is changing from 1 to 2. These are actions and reactions. And if I combine these last two equations, this guy, after I replace du dx with sigma over E, with this equation, with this or that equation, I get this differential equation, second order differential equation, just like carbon nanotube structures. Now, I have to look at the boundary conditions. So if this is tablet 1 and this is tablet 2, the boundary conditions I have will be, I need 4 boundary conditions, 2 for sigma 2, 2 for sigma 1. This is 1 and this is 2. At this end, normal stress is sigma 0. At this end, sigma is 0. This is for 1. For 2, it's the opposite. Here, the stress is sigma 0. This and that put the whole structure in equilibrium. And here, sigma 2 is 0. These are these 4 boundary conditions that can be solved to get these differential equations for sigma 1 and sigma 2 as a function of tau. And keep in mind, the differential equations we're dealing with is that the second derivative is proportional to the function itself. So it could be either sine cosine or sine hyperbolic cosine hyperbolic. It all depends on the sign of this quantity, which in this case, it's positive. So the derivative of sigma 1 is proportional to some positive times sigma 1. The derivative of sigma 2 is also proportional to some positive times sigma 2. Note, there's a minus sign here and minus sign there, right? So then it means the answer is sine hyperbolic and cosine hyperbolic. And these are all based on this length scale, 1 over lambda, which is 1 over length scale. So that our material has the performance of this material in the elastic regime has a clear length scale, characteristic length scale. We can also calculate tau from equilibrium equation. Keep in mind tau was d sigma dx times b. So if I have sigma from here, I can easily calculate tau. This is what we call our equation 6. And it's a very important equation. Equation 6, both components are only valid for the elastic, in the elastic regime, okay? So that so I'll continue